Hi, my name is Sukmani Sethi, and this is my lab report for Physics Lab 5 on the motion of a slinky. As a preview, as stated in the slinky video, the slinky had a mass of 0.20412 kilograms, and the initial velocity and positions were 0 as it dropped from rest, and the final position was negative 0.49 in the y direction because the origin was placed at the start of the motion. So the purpose of this lab is to investigate how forces such as gravity and drag influence the motion of the slinky, and to create a computational model to predict the slinky's motion and compare it to the actual experimental model found using Tracker. Key physics concepts used in this lab include Newton's second law, which states that a force is equal to the acceleration of an object times the mass of that object, and it shows that if there's constant acceleration, the force would be constant as well, which isn't the case here, but we also use drag force, which opposes an object's motion through a fluid like air and increases as the object moves faster, and the drag force is given by the following formula. So the force acts in the opposite direction to the object's velocity, reducing its speed over time. Newton's second law allows us to both derive the velocity update formula and relate momentum to force and time. Using this, we can predict how the mass's speed and direction will change as it moves. Also, we use the concept of static equilibrium, which occurs when an object is at rest, which with the net force and net torque acting on it equals 0, which ensures that there's no linear or rotational motion. So the slinky video was put into the Tracker software to find the values of the motion. These were the graphs and values outputted, and the final position was negative 0.49 in the y direction. In order to create a computational model, the initial conditions were inputted into the code, and the time was found from the Tracker by looking at how long the slinky was actually in motion. And the motion was split up into two parts. The first part was when the top of the slinky was falling towards the bottom of the slinky, and then when the slinky itself was falling onto the ground. So for the first portion of the code, it focused on determining the tension force, which is equal and opposite to the force of gravity, and its effect, whereas the second focuses on the gravity and the drag force of the slinky actually falling downwards. Because tension and gravity cancel each other out on the first part of the motion, the slinky doesn't actually move downwards. And then the update and position formulas were used to calculate the final position and velocity of the slinky after the slinky is fully compressed, because then the drag force and the force of gravity is incorporated to create the final model that's shown on the slides. Then taking data from both the computational and the actual experimental model from Tracker, they were taken to create this graph that compares the two data sets. So as you can see, the horizontal portion of the graph represents the slinky as it was collapsing onto itself, and there was no downward motion there. And then the second half, where it's moving downwards, was when the slinky was actually falling after it collapsed. So the difference between these two models come down to potential errors in the lab, which include the inaccuracy of the Tracker, as the points were estimated by frame, and as well as the camera in the video not being completely stationary could have also affected some of the points. So what does this mean? Due to the tension force and force of gravity, the slinky experiences static equilibrium as it collapses before it experiences the drag force and the gravity force that actually cause it to move downwards. So the model with drag predicted a terminal velocity because the drag force increases with speed and eventually balances the gravitational force, which results in constant velocity, whereas in the first section, the tension force and the gravitational force canceled out, which caused the static equilibrium. So in the velocity versus time graph, the model with drag shows a curve that levels off at terminal velocity. And both the experimental and computational had the same end position of negative 0.49, while the computational showed constant drag, whereas the actual experiment had a less ideal model of drag because of the shape of the slinky. If the slinky was initially thrown downwards, the terminal velocity would be the same in both cases because it's just determined by a balance of the drag force and the gravitational force, which just depend on the object's shape, the properties in the environment, and isn't affected by the initial velocity. But if it was thrown downward, it would reach a terminal velocity more quick due to its higher starting speed.